Hello, this is Dr. James Camp of Lee College in Baytown, Texas, and this is my presentation on common applications of loops in C++. Now, this presumes that you've already watched my presentation on how to program loops in C++, and this is a follow-up on how we can use some of the most common uses of loops. Okay, so what are some of the most common uses of loops? Taking repeated inputs is probably the most common use of loops in terminal type, text interface applications, because if you want to input a list of numbers to grade an average or something like that, you need to input each number one at a time, and the best way to do that is a loop. Adding and averaging numbers, finding matches from a list, finding maximum or minimum values from a list, comparing the previous or next values in a list to figure out when to stop processing a list. And for my engineering viewers, solving the basic equation f of x equals 0 or doing numerical integration are fairly common engineering uses for loops. Okay, so what do I mean by taking repeated input? Well, the idea here is that we want to make some decision that if it's true, we're going to take input and then return to our decision value. And if it's not, if that decision turns out to be false, then we'll continue on with our program. So one way to do that is to use what's called a sentinel value. So let's say we're taking a list of numbers such as student grades that will always be greater than 0, or at least 0. I mean, you can get a 0, but you can't get a negative grade. So if we check the question, is input less than 0, okay, the answer should be no. I put these backwards. The answer should be no if we just got a legitimate grade, and it should be yes if the user was typing what we call a sentinel value, a value that indicates that the list is done. So the prompt to the user might say, enter a list of numbers, enter -1 to end. Okay. Now for this to work, we have to have taken one input before we enter the loop. Okay. So that the first time we reach the decision, we have some input to evaluate and find out if it's less than 0. So presumably the user could type -1 at the very start of the program and end the list right there and never take an input at all. If we don't want to do that, if we want to make, force the user to enter at least one valid entry, we can use a do while loop instead of a standard while loop. But the way this is written, our process would look like this. We create a double value called input. Then we tell the computer while, no, sorry, I forgot my priming step. So this first step here is called a priming input, or a priming step. It gets us ready for the loop. This less than 0 here, that is called our sentinel value. So we might here see out enter grades or -1 to end. Okay. And then we'll cin input. We'll read their first input, and while input is greater than or equal to 0.0, because it's a double, we've got to use a double value there, then we do something to use the current input, and then we cin the next input. Okay. Using the current input might be echoing it back to the screen. It might be adding it to an array or vector or list of values. It might be adding it to a sum that we're going to then divide by the number of entries to get an average. We'll talk about that in a future slide. Okay, another way to do this is to look for a particular condition on the input, which might also, again, be a sentinel value, but to use a Boolean value to keep track of that, and that way we don't have to do a priming input exactly. So the way this works is we start by setting a Boolean value done equals false. Okay, we could do it the opposite way. We could make a value that says still going and make it true. Now our decision says, asks if done is true. No. We take input again and bring us back to the loop. Oh, wait, I missed a step. We take input, and then we check the input to find out if done is now true or not. Okay, then that brings us back to our loop condition. And once we have set done to true, we continue on with our program. So here's one way that might play out. You might have int input and set bool done equals value false. Okay. And then we say while bang done, while not done, then we're going to cin input. We're going to check if cin.fail, which tells us that the last input was not a success, okay? That the input that was read from cin did not match the idea that input was an int, okay? If cin.fail, then we say done equals literal value true. Okay, else we use or store the input number. Okay, the way this works, we're trying to get a list of integers. Okay, maybe we're looking for valid phone numbers entered as integers. And so we set done to false, meaning not done is true. So we enter this loop. We get an input. If the input is an integer, then we fail the CN fail test, and we go right here to where we're going to use or store the input. Add the phone number to our phone book, maybe. Okay. Then we come back to while. Done was still false because we didn't match cn.fail. This time the user enters a blank line, meaning they're done with the entering phone numbers, or they enter a Q, meaning they want to quit. Okay, we come through here. That means cn.fail matches, okay, because we didn't enter an integer. So done is true, and then when we come back to while not done, we fail while not done, and the loop exits, and we go on with whatever's next in our program. We can add or average a set of values by keeping track of a total value. So here I'm not going to do the flow chart. I'm going to assume you understand enough C++ that you can read my code examples. So we're going to set input again as a double that we're reading, but we're also going to set up a double called total, and we're going to initialize it to 0.0. Okay, now while cn to input does not fail. Okay, this is a shorthand for doing input and testing the cn.fail variable. This construct would return true if good input is received and false if bad input is received. So while cn input, then we're going to say total plus equals input, and that's really all we have to do. Then down here we're going to do something to use the total or report it. Maybe we see out total, or maybe we pass total to another procedure that will do something different. If we want to average the values, it's about the same idea, but adds one step of complexity. Okay, so we double input total, and we set total to 0.0 again. But this time we need an int keeping track of how many numbers. It's conventional to call that count, as in you're counting the number of numbers, and we're also going to initialize that to 0. Remember, don't put the .0 on this one because it's an integer. Okay, now while we use this cn.input trick again, while cn to input is a valid double, okay, we're going to, this time we're going to total plus equals input. That's easy. But then we're also going to count plus plus, and that will keep track of how many times we've been through this loop successfully. So as soon as the user delivers bad input, they hit a blank line or a cue for quit or something like that, we'll get skipped out of this loop, and we'll have counted exactly how many times we've written a valid double. So then we're going to put in an if, because it's possible that the user typed bad input to start with. So if count is greater than 0, then double average. Okay, now the compiler is going to yell at me here because I'm creating a double variable inside an if, and that won't be valid outside the if. So I need to create the double variable here, double average equals 0. Okay, now I can say if count is greater than 0, then average equals, average equals total divided by count. And since total is divided as a double, we'll do proper floating point division here, not integer division. So we'll get a fractional number. Okay, then I can see out the average value, or I can store it and use it for later in my program or something. Okay. Finding matches is often a very a common use of loops. Okay. Let's say we want to find the first match. Let's say we've just entered a list of grades, student grades, and we want to find the first student who is not passing. Okay, so find first match to grade less than 70. Okay, I'm going to create a Boolean variable to tell me if I have found what I'm looking for. And since I haven't found it yet, I'm going to set it to the initial value false. Okay, I'm going to create an int to track my position in the list position. Okay, and I'm going to set it to the initial value 0 because we're going to start at the very first part of the list. Okay, so I'm going to assume here that I'm using a vector in C++ or an array list in Java or a list in C# so that it knows how many it has. Okay, so I'm going to say while not found, okay, and list position is less than grades dot count. Okay, that tells the computer to check how many grades are in the list grades, okay, to check the count there. And if our list position ever exceeds that, then we've run out of values. There are no matches. Okay, so that opens my while loop. If grades dot at, I'm going to use the C++ syntax here, list position equals 0. Okay, well, we decided we wanted grades less than 70, so let's do that. Less than 70.0. Okay, we're using double values to store our grades. So if we found one, then found equals true. Easy. Else, list position plus plus. We go on to the next position in the list. Okay. When we're done, then we have an if found. Okay, that's why we used found as a positive variable, so we can make this statement. If found, then we're going to see out student number list position is failing. Okay. And then we can put an else, and if not, we can see out the happy message, no failing grades found. Okay. What if we want to list all the matches? That's actually an even easier loop to write. We don't need to worry about our Boolean found. Okay. So in this case, we create our int list position. Okay. Actually, we probably should over here output list position plus plus because, or list position plus 1, because the user is going to expect the first student in the list to be 1, not 0. Imagine if it said student number 0 is failing, you'd be thinking, what the heck? So for this, we can use the enhanced for each loop. Okay, in C++, that looks like this. For I have to declare it. Double grade colon grades. Okay, works the same in Java. In C#, it would say for each double grade in grades. Okay. Then we're going to if grade less than 70.0, we're going to see out student number plus plus. I'm going to have to wrap this down to the next line. Plus plus list position. We haven't talked about this use of the plus plus operator, but if you put plus plus before instead of after list position, it adds one to list position before you use it. Okay, so that we want to add one anyway to keep going in our loop, so we're going to add one and then output it, and that keeps our user thinking in terms of a list that starts at 1. Okay. And we have an else. We just list position plus plus. Okay. And that takes care of our entire list. And we'll have listed out every student who matched the is failing. Okay, and then we'd want an end line operator there to make sure each student gets reported on a different line. Okay. If we were really clever, we could even have a separate array of student names, and we could list the student name instead of student list position by using the command cout students .at list position is failing. End line. So we could stick that here instead if we have a list of student names called students.
Hey, Dad.
Okay. Another thing we can do in terms of finding matches is count matches. Okay. So this is kind of a silly example, but if you wanted to count the number of spaces in a string of text, or maybe you wanted to count the number of words. That's a little more useful. Okay. We set numWords to 0. Actually, we'll start numWords at 1 because we'll assume that there's one word in the sentence, even if there's nothing there. And then we'll say for. We'll use the standard C for loop this time. Int. It's common to call this I for index. Okay. I starts at 0. I less than we'll call our string str. Okay, or maybe we'll call it text. How about that? Text dot length. Okay. And each time through the loop, we'll I++ to get one step ahead in the loop. Okay. So for each of these integers, we're going to create a string one car, okay, equals text dot substring start at I, go one place. Okay. Then if one character equals a space. Okay, in Java, notice you'd have to use the dot equals operator. C++ and C# allow overloading of the equals operator so that strings can be used with equals. If one car equals space, we'll say or one car equals \t. Remember, that's the tab character. Okay, so if they put a space or a tab between words, we'll catch that. Then we'll say numWords++. Okay, we're going to assume here that the user is not putting double spaces between words or anything like that. So this is not really a very good word counting algorithm, but it shows you the principle of the idea. If we were really doing a word counting algorithm for a word processor, we'd want to add things that detected if the characters were next to each other, or if if two spaces were next to each other, or if the words start with a space, obviously that doesn't mean a new word, and such and so forth. Okay. The other use for a match finding is validating input. Okay, a lot of times you want to keep prompting the user for input as long as they type an invalid number. So let's say we want the user to input a starting date for a loan. If we go back to our loan processing program, you can say while or that's a little more, date checking is a little more difficult. So let's say you want to check for a valid bank balance. Okay, so while input is less than $0, our loan can't have a negative starting balance. I suppose your savings account could have a negative starting balance, but our loan can't. So while input less than 0.0, we'll prompt we'll see out enter a positive value. Okay, and we'll see in a new input. Now if you're paying attention here, you'll notice that we missed the priming input this time, so we'd have to have a cin input up here. Okay. Another very common example is to find the highest or lowest value. Maybe we're sketching through, reading through a list of forecasted temperatures for the day, and we want to find the day's high and low temperatures. Okay. So we have to create values. Let's say we're reporting our temperatures as doubles. Okay. Double high temp equals our starting temperature, double low temp equals our starting temperature. Okay, so instead of start, maybe we have an array of temperatures. So temps at position 0 would give us the temperature at the start of the day. And if it never gets higher or colder than that, then we've got our high and low temperatures. Now, for for int, because we're using array indexes, int I equals 0. Though we really don't have to check 0 since we used 0 as our starting point. I less than, let's say we have hourly temperatures, so number of hours that were reported. Okay, remember, don't use magic numbers in your code. And then I++ to keep us moving through the list of temperatures. Okay, then we have an if temps at I greater than high temp, then we'll say the new high temperature is temps at I. Okay. Else if temps at I less than low temp, and we're going to swap low temp for temps at I. Okay. And we could put an else, but we don't really need one. We aren't going to do anything with the temperature that isn't higher than high or lower than low. And then that takes care of our loop. And at the end, we'll report highs and lows to the user or something like that. Okay. Another use of this technology or this technique is to find, say, the max altitude in a rocket simulation. Okay. we're going to set up all of our variables our initial velocity and speed and time, position and speed and time. And then while while y position, that is our position in height, is greater than 0.0, so while we're still in the air, we're going to do our calculation, calculate new y position, y velocity, time. Okay. And then as part of our calculation loop, we're going to say if y position greater than y max, which will happen all the time as the rocket is going up and then will suddenly stop, then we'll set y max equal y position, t max equal time. Okay. And then at the end of our while loop, we'll be able to output y max at time t max. And then whatever other output we wanted to give. Note I would never actually use a output statement like that. I'd include text like the rocket reached y max meters at time t max seconds or something like that. I would always give more information than that, but I'm running out of space on this slide. Okay. A variation on this is finding adjacent value, comparing adjacent values. So let's say we didn't want to waste our time calculating the rocket's path back down to the ground. We just wanted to know the maximum altitude. We'd create Boolean going up, and we'd set it to the initial value true. Okay. Then this time what we'd have to do is have double y position and y previous. Okay. And so we can show an example of a do loop here. We've been using fors and whiles this whole time. We can say we're going to calc new, oh, sorry, missed a step. So first, y previous equals y position. Okay, so whatever we're going to have to initialize going to have to set up initial values for y position and launch height and launch velocity and that sort of thing. Then we're going to calculate new y VT like we did on the previous slide. And now we can say do this while the new y position is greater than y previous. Okay, so this will kick us out of the do while loop as soon as we calculate a new y position that is less than or equal to y previous, that is, as soon as the rocket starts to fall back to Earth. And then you can report the max height as y previous, because that was the highest point. Y position is now either equal to or one notch down from y previous. Okay, got a couple more examples. Solving for f of x. Okay, we can assume, if we can assume that the function f of x crosses the y-axis at exactly one point between points x1 and x2, and that f of x1 is less than 0 and f of x2 is greater than 0. It works if it goes the other way too. If one is, as long as one of them is less than 0 and the other is greater than 0, this method will work. Okay. Then we can say double x high equals whatever our value for x2 was, and x low equals whatever our value for x1 was. Okay. So we initialize those to our two bracketing points. Okay. Then we create double f high equals, assuming we've defined a function f of x high, and f low equals f of x low. Okay, we'll talk about how to define your own functions in a future presentation. Do x mid, the midpoint between the two. So we're going to go halfway between here and here, which is roughly right there, which is closer to the solution than either of the other points. X mid equals x high plus x low over 2.0. Okay. And f mid, I have to have declared these up here. I forgot to do that. Double x mid, f mid. Okay. F mid is f of x mid. That's easy. Okay. Now, the key point, we're going to check if the sign of x mid equals the sign of x low. That means they're both negative. They're both on the same side of the line of the x-axis. Then we're going to replace y low, I'm sorry, x, we're using x. X low equals x mid, f low equals f mid. And I made a mistake here. It's not x that I want here, it's f. Okay, that makes more sense. Yes, if the sign of the function of x2, of x mid, okay, we've got f of x mid here. If that is on the same side as x high, we want to replace it with x high. If it's on the same side of x low, we want to replace it with x low. Okay. Else, we don't need an if because the other option is that that f of x is on the other side. X high equals x mid, and f high equals f mid. Okay. And we do this while the absolute value of y mid is greater than some really small number, say 1.0 e negative 12. Okay. Doubles can go down to about negative 15 or so in precision, but we don't feel like maybe we need that much precision in our solution. So, so you could. So the way this works, in case you don't believe me, as drawn, we check this is f low, this is f high, this is f mid. We check here if sine of f mid is equal to sine of f low. That's positive, that's negative, so we skip out of that, go to the else. So now we replace x high. So the new x high is there. And now we go back through the loop, and we'll get a new midpoint. Okay. Use a different color this time. We'll use green. So now x mid is there. F mid is there. Now this time it's sine of f mid is negative, sine of f low is negative, so we're going to go here and replace x low. So now this is the new x low and f low, and this time pick another color I haven't used. I'll pick red. We go in between those 2 points and we land pretty much at the intersection point, if I drew this correctly. Now, it doesn't always resolve this in as little as 3 passes through the loop, but if it does, you're golden. Okay. If not, you have to go 3 or 4 or 5 or 6 times through the loop. But anyway, it's still a lot easier than trying to calculate this out by hand. My last example of loops is a common engineering problem called numerical integration. Okay, let's say that someone at your company designed an airplane wing that has this shape. Okay, and you want to know the exact area of this airplane wing. Well, it's obviously a construct of multiple curves, which may have, maybe you know we'll say for now that you know an f of x that describes this, but maybe it's made up of multiple curves, multiple stepwise functions, and it would be very difficult to integrate by hand. But we know that the definition of the integral is taking the sum of all of these pieces where each bar is delta x wide, okay, and taking the limit as delta x approaches 0. So integral from x min to x max, integral from x min to x max of our f of x times dx, which is this limit of delta x as delta x approaches 0. For sufficiently small dx, this is approximately equal to the sum of f of x times delta x, okay, from x min to x max. So we can do this with a for loop. Double integral equals, started off at 0.0, okay, and double dx equals sufficiently small number, say 1.0 e negative 6. Okay, we can actually go much smaller. We can go e negative 15 if we want to. Okay, that'll use a lot of steps to do the integration. Terribly inefficient, but it would get us the maximum, or it would get us something that would truly approach limit of delta x approaching 0. There are other tricks we can use to get a better integral without having to go that small, but for now let's do that. So for double x equals x min, whatever we decided our x min was, okay, x is less than x max, whatever we decided our x max was. Note we want that to be a less than and not a less than equal, because we'd be double counting if we included x max. And for each step, x plus equals dx. Okay, and inside that for loop, all we have to do is say integral plus equals f of x times dx. And then at the end we use or report the integral. We might see out something like area of the airplane wing is blank square meters. We can get away with using a smaller, a bigger step, 1.0 e negative 6 or negative 9 maybe, If we do trapezoidal integration instead, where we say for, same stuff, okay, but this time we say integral plus equals f of x plus f of x plus dx over 2.0 times dx. What this does is it says we take each of these boxes as if it's a trapezoid and say f of x and f of x plus dx. We kind of average the two values together and we integrate that way. That's easily much more accurate than the stepwise integration that we used in the first one. And there are even more accurate procedures that assume that use the curve of the curve, the curvilinear nature of the curve. Okay. All right, some closing thoughts. So you've seen so far that we can use loops for a lot of functions. It often comes down to the question, are we done yet? Okay. No. Keep going. Yes. Go on with our program. Report results, for example. The priming, the sentinel values and Boolean values that we looked at, the checking for the first match in a list, or the checking for the point where the next value is no longer greater than the previous value. Those are all examples of that kind of loop. Another example is one where we have basically go through a list. Okay. And if we're still going, we're going to add. We're going to check to see if we've got a new maximum or minimum value. We're going to do something, check to see if we have a match. Use the value if it passes our check, and then we come back, and when we're done with the list, we move on with our program. We report results. We do something. Okay. This one, the are we done, of course, lends itself very well to a while loop. The going through list lends itself very well to a for loop. Okay. I think you have a good idea now how to use loops, and we're ready to write some really useful programs.